Students, so now we will continue recording a controller system design using body plot or frequency response analysis. So last record I was mentioning understanding body plot, and today lecture I'll mention to you this series of video using body plot. And if you click on it, you'll find actually 5 series which I really recommend you to go into the Matwork Tech Talk and really go over them short videos talking about the use of body plot, and basically it's design using body plot, controller design, as this part 5 showing you controller design using body plot. Here is showing to you lead and lag compensator in the frequency domain. We already saw them in the time domain using root locus, so here in the frequency domain. Explanation of the phase and gain margin, why we should be above 180 degree, minus 180 degree, and below 0 decibel for phase and gain margin. It's came from Nyquist plot and so on. So here, like, they explain a little bit why that's how it's stable. So explaining about the meaning of gain margin and phase margin, which we already introduced. Talking about the open loop shaping, but first starting talking about closed loop systems are really important. I'll point to you the open loop shaping actually. Everything else, I guess, you will be able to see it somewhere, or we already saw some of them. But open loop shaping is really here the focus, because based on it we will go on controller design later on. So what's this open loop shaping? As an introduction to open loop shaping, let's first refresh our memory a little bit about what we previously did in intro to control chapter. Like when we're having block diagram this way, you have your reference R and your output Y, and you have disturbance, and we said because it's a linear system, so Y output is a summation of the two input transfer function. So then we said basically Y is equal to Y1 plus Y2. In the first one, we take the disturbance equal to 0, and we find the transfer function Y1 over R. And in second one, we take R equal to 0 and find the transfer function Y2 over D. Alright, and so that's the function that we find for Y1 over R. It's CGAP 1 plus CGAP GS. So basically CGAP is the forward loop over 1 plus the open loop, or this open loop transfer function CGAPGS. And what for Y over D? It is P over 1 plus P GSCGA. And if you look to the denominator, both denominator, if you remember, they are the same denominator. There's a difference, like here is the transfer function over the disturbance, output over disturbance. The denominator is the plant, only the plant, which is here. Okay, so those, they have the same common denominator, 1 plus the open loop. Alright, so this is a good refreshment of. And then Y, if you want, Y is basically gonna be Y, the transfer function times R plus the second transfer function times D. Actually, those we'll find now in a while, they have a name. This transfer function, it has a name, and this transfer function also, it has a name. But remember how they look like. The denominator is the same. Also, we gave the example of another plant, assuming that you have, in addition to the disturbance, you have noise. So your input is V desired, your output is V. Then also you could find V, which is the summation of the output that came from the desired input, the disturbance input, plus the noise input. Alright, plus the noise input. So you have three input in this case. transfer function times v desired plus transfer function times d plus transfer function times n, and this transfer function is something we determined before and just as a refreshment. So I was determining v over n actually in this exercise. Alright, also I determine v over v desired. So you look here, it's a very important thing. V over v desired is how it looks like, or k over k plus b ms. So this is the standard basic form of a first order system, and v over n. So I want you to see both together, how they look like. So v over n and v over v desired, they have only minus difference in between. So that's the only difference between, if you wish, actually between v over v desired and v over vn. So the minus, that's mainly the difference in between them. So keep that, but the denominator is the same. So they have same denominator as well. And we saw before that v over v desired has same denominator as v over d, but the difference in denominator, as we saw just in a while. So here we are seeing also that v over n and v over v desired, they have same denominator also, but minus in denominator. Okay, this is an important finding. So after this refreshment, let's go. So here let's see the meaning of those transfer functions. Okay, that's my system. Here I changed it a little bit. I changed the system. My plant is here. I put my disturbance here. It's alright, so you can put it here and you get slightly different transfer function. But in general, so you know now how to get y function of the reference input, noise, and disturbance as 3 inputs. So reference and the noise, they share the same transfer function except the minus, as you can see. The disturbance also, they share same denominator as we saw before. So then was, if you remember, this transfer function for the reference, it was what? It was forward over 1 plus loop. So the loop is, or forward over 1 plus the open loop transfer function. So say here it was the transfer function after the disturbance. So here in this case is 1, nothing after, 1 over same denominator, 1 plus PC. See, you can do the calculation, but here just I did the analogy. Essentially, what I want to tell you is that this transfer function, we call it the sensitivity. And this transfer function, we call it complementary sensitivity. Why complementary sensitivity? Because simply, if you add them together, I mean, you take common factor 1 plus PC, you will get PC plus 1 over 1 plus PC. So, 1. That's why we call it complementary sensitivity. Or sometimes we call it transmissibility. That's why the letter T. We call it transmissibility transfer function and sensitivity transfer function. And if you get the transfer function which is related the error to over the reference input or disturbance or n, you'll find they are same transfer function with the letter minus, with a minus difference. So that's why if that's my output that I'm interested on is the error, and I have 3 input in my function, so my interested output now is not y, so I want to compute for e. So then I have 3 input r, d, and n. You have 3 transfer functions, so you add them together. The same methodology, you cancel d and n, and you keep only r, and you do e over r, etc. You do for all, and you add them together. You end up having this, so which is the sensitivity matrix. Okay. sensitivity transfer function. What those are? So, and why do we need them? Well, basically, because here you have reference and noise. So ideally, what I want to have good tracking at low frequency. I want to have my transfer function PC over 1 plus PC looks like this red curve. Okay, this is if you want to have good tracking for R. If you want your Y to good track R, you should have this DC gain, which is 0 decibel at low frequency. What that means? That means if 0 decibel means the output equal to the input, means I'm tracking my Y is tracking your desired input. Alright, and if you really want noise rejection, and the noise which is normally at high frequency, you should have very high attenuation, good attenuation at high frequency. So if then your PC over 1 plus PC looks like this, means you have noise rejection and you have reference tracking. That's what it means. So ideally, I want to design a controller to shape my root locus in a way like PC over 1 plus PC looks like this, because in this way I can good track my input and I can reject my noise, which normally the noise are high frequency, and your input is most likely it's a low frequency. It's your signal which is low frequency compared to noise. And by looking to the sensitivity also, I wish to have a 1 over 1 plus PC Bode diagram or transfer function that gives you a Bode diagram look like this. Why? Because ideally you want to reject disturbance. So rejecting disturbance means what? Means disturbance is low frequency signals, so you want to attenuate at low frequency. So that's why your 1 over 1 plus PC, you desired it to be like this, looks like this, because in this way you are attenuating the disturbance, you are rejecting the disturbance. So then now you have two goals. You need you to have your complementary sensitivity matrix look like this to track your reference and reject your noise, and you desire to have to shape your 1 over 1 plus PC to shape this how, because you want to reject the disturbance at low frequency, which is your disturbance. So of course I repeat again telling you those data I recommend you to go and look at them on here. So I take them from here, from this presentation, so it's better to go also and look to this small videos. Okay, but here is like my way of explaining things, but somehow similar. So if you look to these two curves, what's the common thing? Is PC. PC is the common thing between these two curves. And PC is what? If you go to the PC is your open loop transfer function. So if you have here H, so gonna be PCH, as you remember the first example I gave to you. Okay, so then PCH could be as the example I gave to you, right? So then it's the open loop, it's not the forward loop as this example, it's in general, it is the open loop transfer function, CP times a sensor transfer function if you wish. So here in this case it's CP is your open loop transfer function. And the goal is, the good things if you wish about PC is you reshape the Bode diagram of P with a controller to your desired goal. So what you do, you design a controller to reshape the Bode diagram as we designed a controller to reshape the root locus. So here we design a controller to reshape the open loop transfer function. Okay, so that's the basic idea about controller design using frequency response, is to add a controller. And we know in decibel, in logarithmic scale, multiplication is adding the curves together, right? So then you need to design a controller C in which you reshape the open loop transfer function to your desired goal, to your desired specifications. So here, of course, on this plot, you can extract the gain crossover frequency, which is at 0 decibel, So you have omega C. Also, you can extract the frequency at minus 180 decibel. Of course, you can know the phase margin and gain margin, and the phase margin as well. Well, in this example, let's first compare the open loop, which is PC in this case, the body diagram of the open loop, this given open loop, to the transmissibility transfer function, or the complementary sensitivity transfer function, which is 1, like here you can see both, 1 over 1 plus PC. Sorry, it's PC over 1 plus PC. This is a transmissibility transfer function. So to compare both together, drawing the body diagram basically of both of them, let's consider the case when PC too much bigger than 1. So then neglect the 1, then T approximately equal to 1, and therefore the body diagram of 1 is asymptotically 0, right? That's how we draw body diagram. Then we take the other case where PC very small in front of 1. If PC very small in front of 1, that's at the end mean you neglect PC, you keep 1, so PC over 1 is PC. And therefore at infinity, the transmissibility transfer function is similar to the PC transfer function. At 0, at low frequency, it is at 0 decibel because 1. And maybe you have maybe in between, it looks like this. Okay, also for maybe alright, maybe it is like this at minus 90. Okay, so that's as comparison between both open loop versus complementary sensitivity transfer function. Well, also let's compare, so we'll see why we are doing that, and let's compare PC or open loop transfer function to the sensitivity transfer function. Maybe I put this here and this is close to it as well here, and in the same way, when PC it's very high compared to 1, very big compared to 1, then it's equivalent to 1 over PC, which means in logarithmic scale it is the inverse of PC, right? It is the inverse of PC. Like if I want to draw it in yellow, I don't have yellow, maybe here it's yellow. Okay, so it is the inverse of PC, so PC is how, then it is this way. Also the phase is the inverse of PC at low frequency. At high frequency, 1 over 1 plus PC, when PC actually smaller than 1, very small compared to 1. You see, 1 PC is very small compared to 1 at high frequency. At high frequency, it's very small compared to 1. At low frequency, it's very big compared to 1. So it's at high frequency at the end. What's happening when PC very small compared to 1? Then 1 over 1 is approximately 1, and therefore at high frequency, logarithmic of 1 is 0. Okay, so it is 0 degree as well. And in between, of course, maybe 45 here, and here maybe it has some peak. Okay, that's how it looks like. So why we are interested on doing this comparison between open loop versus the complementary sensitivity or the sensitivity term, because we just explained in a while that the sensitivity and the complementary sensitivity are important for us to know if we are really tracking the reference and we are rejecting the noise and disturbances, right? And we said ideally we want PC over 1 plus PC to look like this, right? If you want low pass filter, okay, or high pass filter for the disturbance rejection, and if you look at it, it is somehow this way, okay. That's how it looks like. So means a PC shape like this, it's a good design. Good design if you have PC shapes like this, because this is at the end, this PC that I have, it gives me a good transmissibility and sensitivity transfer function. So the complementary sensitivity or transmissibility and sensitivity matrix, that's how we are desired to have them, to have good reference tracking, good noise rejection, and good disturbance rejection. And if you look to the yellow curve and the red curve, somehow is as desired. Therefore, we can say this PC that looks like that, it's a desired shape that I wish to have. It's a desired shape that I wish to have. Okay. So here in this graph, in this figure, we are putting the sensitivity and transmissibility or complementary sensitivity Bode diagram on same plot. In addition to the open loop Bode diagram, we are putting all of them on the same plot. And we know that in order to have good tracking and good disturbance rejection, we need to have a DC gain below above 0 decibel. You need to have again a magnitude above 0 decibel, so that's why you have good tracking. We know that if we have integral, means at low frequency it's infinity gain, you have 0 steady state error, means very good tracking, because 0 steady state error, so pure integrator. Okay, so high gain will lead to a good performance and noise rejection. So that's a rule. First one, good performance, we should be in this zone then. We should be in this zone to have good performance. Basically what we mean by good performance means good tracking and good disturbance rejection. And why up to here? Basically we want to say like good gain, high gain, we need to have high gain at least a decade below the crossover frequency. So the crossover frequency, if it's here, so omega c over 10, so like somehow here, okay, so a decade below the crossover frequency, you should have high gain in order to get good performance system. That's the rule number one. Also, to have a robust system, we know that we need to your sensitivity matrices like this, or sorry, the transmissibility matrix, which is reflecting by the noise, so the noise are completely attenuated, so your system is robust. And also the disturbance are not amplified. Well, here you don't talk about disturbance, because disturbance usually low frequency, so at high frequency we mainly concern main concern is the noise, and we should be in this way at least. So you should be in here, better to be low like this to attenuate completely the disturbance, and therefore my system is robust system. So I should not overpass the here, like otherwise I'm amplifying my noise. if I'm above 0 decibel. So should be always below 0 decibel at high frequency, and as below as better. This means I'm more robust. My system is more robust. So also again, decade above the crossover frequency, we should be with a very low gain if you wish. So to attenuate, very high attenuation, at least decade below, decade above the crossover frequency. So this is the crossover frequency, which is at 0 decibel of the blue curve. Alright, so that's basically our let's say our design goal is to have good performance and good robustness. So that's the ideal shape to have. We need to have high gain at low frequency for good tracking, and low gain below 0 decibel at high frequency to reject disturbance. That's the basic rule. So high gain at low frequency for tracking and reject disturbance, and low gain or high attenuation at high frequency to reject noise. So that's as simple as that. High gain, we know that the gain, as in PID controller, the high gain improve the performance, the tracking of the system. But if you have pure integrator, means infinity gain at low frequency, so in this case your system has zero steady state error, so very good tracking, excellent tracking. So eliminate the in this case we are eliminating the steady state error and also rejecting the disturbance. Remember, integral effect, pure integral, reject completely the disturbance. So let's explain why. Because at low frequency, remember 1 over s, it has infinity. So that means a very high gain, so good tracking, good performance in general. Reference tracking, good, so zero steady state error, and eliminate the disturbance, reject the disturbance. And at high frequency, it should behave like this, because your system will reject noises as well. Okay, so that's how it looks like a good system. Of course, we say well below the decade below the crossover frequency, decade above the crossover frequency. That's as a rule of thumb. So now the question is how to design a controller C to reshape PC in a way like this, in a way to have good performance and good robustness. So what type of controller you could design? Basically you have, we know PI, PD, and lead lag compensator, PID, lead lag compensators. All of those we can add them to reshape the body diagram to have our desired characteristic, good performance and good robustness. As in this example here, you have a lead compensator. So why it's a lead compensator? Basically, if you draw, as we saw before in root locus, if you draw the S-plane and you look to the poles and 0, you have, it has a 0 at minus 10 and it has a pole at 100. So 0 dominant, so that's why it's a lead compensator equivalent to PD. Okay, that's a lead compensator. Also, if you look to the lead compensator in the frequency domain, so it's equivalent to PD. In the frequency domain, it has, if you look to the phase, basically between the pole, between 10 and 100, that's 10 and 100, it has a 90 degree, and then above and below it is 0 decibel, 0 degree. And here is the at 10 radian per second, so you have 20 decibel per decade slope. Then at 100 you have minus 10 decibel per decade, so plus minus, so it returns to 0 decibel. Alright, so this is expected. So here it should go to 90 at 0. Then here it should go to minus 90. So 90 and minus 90 returns back to 0. Alright, so that's basically how it is the shape of C controller lead compensator. So then C, so now you need to add to your plant a shape like this. So means you increase the phase in here in this way. Otherwise it is 0. But in between the 0 and pole, it's 90-degree phase in this case. So this is a lead compensator. This is a lag compensator. So as you know, a lag compensator, so you could add a lag compensator to your plant to reshape the body diagram in different ways. So here you increase the 90-degree. So then here, if you look to that, you have a 0 at 100 and a pole at 10. So it is more like PI. So integrator, so the pole, so the integrator term dominate. Okay, and same at 10 rad. So inversely reverse to this one actually. So at 10 radian per second you have minus 20 decibel because it is integral factor, and at 100 so plus 20 decibel per decade, so it returns to 0. Also it's minus 90-degree in between 10 and 100, so minus, so you reshape your plant this way. And what's the advantage for each one? Lead compensator adds phase lead, and therefore improves phase margin, because you add phase lead, so you improve the phase margin. So then you improve speed, you improve damping. Okay, let's improve phase margin, improve damping, speeds up response, and you speed up response. That's the advantage of lead compensator. By adding this, actually what you are doing is you are improving the phase margin, improving the damping, and you are speeding up the response, make your system faster. That's the advantage of lead compensator, or when we need to design a lead compensator, to improve the phase margin, improve the damping, and speed up the response. So later on in a while I will connect you the time domain to frequency domain, so you'll be able to look at both. But basically that's how lead compensator is. Lag compensator adds phase lag minus 90-degree. So improve disturbance, in this case improve the disturbance rejection, because high magnitude, not low magnitude, so add a magnitude. So improve disturbance rejection but slow down the response of the system, because adding phase lag. So slow down the response but improving disturbance rejection and improve tracking. That's about PI control. So you could add lead compensator, you could add lag compensator, you could add PI compensator. So Kp plus Ki over S, and this one drives steady state error to 0. Eliminate steady state error, drive to 0, and improve the disturbance rejection, like the case of PI. Kp over Ki over S. But you see it's at low frequency infinity, the integral term. But this is how to draw. If you want to draw the body diagram of it, you cannot draw it this way if it is in this form, because you have plus. So you should have multiplication. We need to convert it to our basic form in which you can draw the body diagram, right? So I can write it actually this way. Like if you take, for example, S, so you have KPS plus KI. So now if I take KP common, for example, so I get S plus Ki over Kp over S. So this, if you wish, similar to this. Look at both. Look at both boxes. They are similar. So that's your C. Constant, some constant S times S plus a factor omega z, and this is a basic form we can draw now. Okay, you have pure integral and you have derivative factor. So at omega z, if you have proof integral at omega z minus 20 plus 20, so you get it like this. So that's a pi compensator, and if you look at it, it doesn't behave as a lag compensator. If you look to the Bode diagram of a lag compensator, it's not exactly as pi compensator. You see, this is a pi. That's how it is, so we can see it this way. Same, we can have PD compensator, and PD compensator, it adds phase lead, improve phase margin, improve damping, and speed up response. So exactly same as a lead compensator. So also this, we cannot keep it this way. We need to, if you want to draw the Bode diagram, we need to convert it to a common form, a multiplication, if you wish, multiplication of basic form. So you look at how it will look like. Well, first here what they did actually, they add a filter to it in a way, like, numerically integrating a derivative, it's not stable. Differentiation is not stable, so better to add a filter, which is a low pass filter, so you'll cut off the noise of high frequency as well. So instead of being like this, you will be like this. Okay, and this is how to write it in basic form to draw the Bode diagram of. We can do it this way, take S plus n common, and this is like p, so you can factorize it, so you get finally something like this, and you get at omega z and at n. So then you can draw the Bode diagram of it. Okay, and this is the PD compensator. So if you look to the PD compensator, and let's put it with a lag compensator, for example, with a lead compensator. Okay, let me take this, Control C, put it here, and look at both curve, like here. Look at PD compensator with a derivative effect, with a filter added on it, low pass filter, S plus N. That's how it behaves. And look at lead compensator, they actually equivalent. So see, basically then a PD compensator with a low pass filter added on it to cut off the noise at high frequency, it's equivalent to a lead compensator. So now you can see them. So it is basically the same, right? So with the difference of having a gain here. Okay, you can always add a gain to your system. But a lag compensator, if you want to compare it with PI, I can take it up a little bit. It is not exactly the same, because here it will eliminate the steady state error. Here it's improve damping, speed up response. So because here you don't have high gain at infinity, you have good gain, 20 decibel. It's not like zero, but it's not like infinity or very high gain. So that's why PI controller it's like this. But also PI controller, it's not energetically or computation efficiency is not as good as lead compensator. But now because of speed up memory and calculation, so then easily we can integrate an integrator, PI controller. But PD is still not the case because the noise and so on, better to add low pass filter. So then lead compensator is used in the case of PD, and PI better than lag compensator. But you can still add lag if you want to have more computational efficiency, less energy consumption if it's analog implementation. Now, one important step in controller design in frequency response, to design a controller in frequency response, after knowing all this type of controller, lead lag, PIPD, lead lag, and PID, knowing all of them is important. But one important step in designing controller in frequency response is to know the relation between time domain and the frequency domain. Okay, and like here, so we'll see what's the relation between time response and frequency response. So is there any relation between the time response that I can see and the frequency response? Let's consider this frequency response and this time response and try to see the relation between both. First, here, what you can see here in this circle is reflect is in frequency domain, which is the low frequency response, the low frequency magnitude in frequency domain represent the steady state in time domain. So that's the time domain response, and that's the frequency response. And here is open loop frequency response. So open loop, we know the open loop, and here is the closed loop time response. So whatever you have here in open loop represents your steady state. In another way, I can say higher DC gain reduce the steady state error, and this is, we know, we already saw it before. So if you increase, like take the example of infinity gain for integrator, pure integrator, this will eliminate the steady state error, right? Because it has very high gain at low frequency, infinity gain at low frequency. So now hiring the gain, or if you multiply by high gain, you increase the magnitude, decibel magnitude, this will reduce the steady state error. So then the first link between closed loop time response and the open loop frequency response is to know that improving the gain will reduce the steady state error. So you remember your complementary sensitivity matrix and sensitivity matrix, right? And remember what we said just now, like we are planning to design a controller. So to know which type of controller we need to design, so you need to be able to link between time response and frequency response. So now if that's assuming the plant behavior, so then I can know which type of controller I need to add. For example, maybe simple gain could be fine because I can increase the gain and therefore reduce the steady state error, and then this is fine for me. So then to know which type of controller you need to implement, it's important to link the frequency response behavior to the closed loop time response, open loop frequency response to the closed loop time response. We know we design an open loop as we saw in a while. So then that's the first thing you can draw. Low frequency gain reflect the steady state of the system. Second is the crossover frequency. We know at 0 decibel is here, then from here to here you have phase margin, right? And this is the crossover frequency, and here is the peak resonant frequency. Okay, it's crossover frequency or the peak resonant frequency is your natural frequency, the frequency of the system, assuming they are very close to each other. So what this leads to what? You know, if you have high peak, remember high peak means what? High overshoot. If you have high peak means high overshoot. Remember, maybe here high peak corresponds to high overshoot, low damping, means low damping at the end, low damping ratio. And this is a relation, right? And here is the relation. We said usually, okay, MR approximately 1 over 2 zeta. We said 1 over 2 zeta. So then, if in frequency domain the peak increase, it reflects to decrease in the damping ratio or increase in the overshoot. Okay, so this is this one also link between time domain and frequency domain. Also, we said just in a while you have the phase margin, right? And also a high phase margin means, if you wish, high phase margin means in frequency domain low overshoot. If you have good stability, good phase margin, so you have low overshoot. Okay, high phase margin leads to low overshoot and frequency. So you can know now, if you design a controller to increase the phase margin of the system, so you'll be having in time domain low overshoot. If you will have higher peak, high overshoot. Okay, so low overshoot, or if you wish, high damping ratio. So this is second. 1, 2. Third is if you move the crossover frequency in this direction. This leads to what? If you move your crossover frequency in this direction, this will lead to a faster response in time domain. And you remember that when we was showing you this example here, when you increase omega n, which is the natural frequency of the system, close to the, which is the natural frequency of the system, or the crossover frequency. Actually omega n is the crossover frequency. You see the response becomes faster in time domain. See, slower, faster. Good. So then this is, if you shift the crossover frequency to here, then you speed up the response in time domain. Those are important, as those three things are important in how you relate the time response to the frequency response. But also other things as well, like remember the low frequency behavior, it indicates what in time response? It indicates, it give you, if it is constant, means it's type 0 system, so you can know the system type. If it is 20 decibel per decade, minus 20 or minus 40 decibel per decade, remember the interpretation like here, it is system of type 0, system of type 1, so from low frequency behavior, system of type 2. Also we can know KP, KV, so the static position error constant, velocity error constant, and acceleration error constant. We can compute them. And computing KP, for example, for system of type 0, it returns to knowing the DC gain. Okay, which is 20 log of KP. KP is equal to K, the DC gain. Okay. That's basically all regarding the interpretation. So here they are written for you, like open loop Bode indicates closed loop time response properties. One, you have steady state performance or transient performance. For steady state performance, larger DC gain reduces steady state error. We just saw it, right? Larger DC gain will reduce steady state error. DC gain of type 0 system can be identified by the magnitude at small frequency, of course. We already saw it just now. Slope of magnitude at small frequency also indicates system type. Okay, those are the relationship at steady state. What about the transient performance? Smaller resonant peak and larger phase margin, as we saw in a previous slide. Smaller resonant peak. If the resonant peak is small and larger phase margin, this indicates what? Smaller overshoot. And also larger gain crossover frequency indicates what? Faster response. Just as transient behavior, if you wish. Okay, those are the relationship between domains: closed loop time response and open loop frequency response. So now, knowing those is an important step, as I said, for controller design. So after introducing all of those, it becomes easy to understand now how actually to design a controller in frequency domain. So we have basically 4 steps. Alright, we have 4 steps. Step 1 is to analyze time response behavior, determine deficiencies. First, you analyze time response behavior, and so you'll be able to analyze, and doing that you can determine the deficiencies. Second, plot open loop system frequency response. Step 2 is to plot open loop systems frequency response in the for the open loop system. Then third step, you add controller Y to change shape of frequency response plot. Which plot? The open loop, to change the open loop frequency response. That's a closed loop. Okay, you add controller because we work on, as we understand from everything we said until now, we work on open loop. So then we add controller to reshape the frequency response plot. And then we iterate to achieve our performance. As in this example here, like assuming as example, as there is no numerical calculation, but just like here, simple example to tell you. Step 1 is to draw the time response. And remember, analyzing time response determines efficiency. So assuming you analyze the system, and then you get, okay, the system is too slow, so I need to speed it up. And maybe you find the system is too much overshoot. So then first I need to speed it up. So if in the frequency domain, so I know I need to shift it this way here. So if I shift it here, so then I'm able to speed it up. So I design a controller to reshape it to relocate this way. So also, if it's too much overshoot, I understand, like if it's too much overshoot, how to reduce the overshoot? We need to increase the phase margin. So instead of having the phase margin here, maybe we have it here. Improve the phase margin and reduce the peak. Also, this is improve the overshoot. So maybe one of them I use, or I use both. If it is assuming steady state error too large as well, so then I need to add a gain, amplify it here. So then I reduce the steady state error. So that's why this is the first step, and so I need to move to reshape it this way here, here, and then here maybe. So to make it faster, phase margin, and improve the phase margin to reduce the overshoot, and improve the gain at low frequency to reduce the steady state error. So that's why we said at the beginning it's very important to understand, link the frequency time response to frequency response. So analyze time response behavior, determine efficiency. Then plot the open loop system frequency response. So then you plot, that's step 2, open loop frequency response. without the integrator. Step 3 is without the controller. Step 3, you add the controller. So your open loop becomes the plant, for example, plus a sensor dynamic if you have, plus the control, plus, and because it's logarithmic scale, actually it's time. So then you iterate to satisfy your requirement, assuming you have some requirement. So in this case, it seems like adding lead compensator, which we know now how the shape of it look like, which is equivalent to PD somehow, but PD with a filter, as we know. So then doing it, it seems like I can speed up little bit. So at the end, I'm reshaping my system. So now we do an example in MATLAB to see how things are going, how we design it. But simply know that I'm reshaping my system in this way, for example, to achieve my design requirement. So let's go and do a design example using the CISO tool in MATLAB. Well, let's first see the example taken by MATLAB, the part 5 you saw in here. If you look to the part 5, basically you have a DC motor and you want to design a controller for it in frequency response. Okay, so you have some specification. They need zero steady state error, maximum overshoot equal to that, maximum rise time, so some speed. So you have some speed, you have overshoot, so this is phase margin, reflect phase margin, this is reflect the crossover frequency, settling time, so also like how fast it is, gain margin and phase margin. That's how in frequency response. So based on this performance specification, you need to design a controller. So speed control, so for a DC motor. So we know the transfer function of a DC motor, speed control. We did it many times when designing a PID controller. Your mini project basically was on the DC motor control design. Also your lab 1 experiment in the experiments you did in lab 1, also same. So here we do frequency response analysis. Okay, so basically you can go with him here. Went to the control system designer app. You have this system, so you can get transfer function of it, and then draw in here the reference and the desired. This is the desired reference and this is the output. So it is for a feedback controller of 1. So then what they are doing here, so see they are showing you in the plot the open loop transfer function now without adding, that's the open loop without adding controller. So then he will start adding controller. He's showing you also the transmissibility and sensitivity matrix, which is the complementary sensitivity and the sensitivity matrix to see the performance, and the time response also to check your requirement that you have in frequency and in time domain. So you have here illustration. So what he's going to do, he drag it to increase the gain. You see it's low gain, DC gain at low frequencies. So that's why you have steady state error. Okay, so then first thing, maybe he need to increase the gain. See by dragging it how the performance will change, and you have a good behavior, let's say for the T and S. You know, we know what's good T and S should looks like, the shape of them. So now we can design a control to reshape them to have our desired requirement here, to have a system APC desired, okay, etc. So we may think to add, like here the adding pole somewhere. So adding, actually they will add a compensator. Let's see which type of compensator he could add. He's adding. So you could follow the, yeah, for example here it's a lead or lag compensator, so the pole is dominate, so it is then it's a lag compensator. Okay, so that's the system. So you can adjust difference between the pole and zero. You modify your system to get the desired sensitivity and transmissibility matrix, reduce the overshoot, etc. Okay, so you can follow here really the link to see how is doing them to verify to get the required design requirement, and at the end he get that system pure integrator and lead lag compensator. Pure integrator, he did pure integrator, in addition to it a lag compensator for the system. Yes, actually lead compensator. Okay, pure integrator and lead compensator. So why it's lead? Let's see. Let's go back and yeah, sorry, because actually lead compensator, because zero is slower than the pole, zero is dominant to, is closer to the imaginary axis. But here, remember, this is the frequency axis. It's not like a plain real axis. No. So the zero is closer to the imaginary axis because it is smaller than the pole, and you can see it here. The zero is smaller than the pole. Yeah, it's smaller because here is 1 over 1 over, so 1 over it. Okay, so maybe that's the form in which it's written. So yeah, then you look to how the tracking is. So this example we'll see later on many examples using the CISO tool, of course, but just now I wanted to point out the example on MATLAB. Also some other interesting example, I recommend you to go over them in addition to what we will do. So DC motor speed simulink modeling, you can go over it in Michigan control tutorial. So DC motor speed, that's the modeling, simulink modeling for it. Controller design, so interesting, you could look at. And here they do lag and lead compensator and compare the control effort for both lag and lead compensator. Alright, here actually whatever here is you do after doing root locus controller design and frequency domain controller design for a DC motor. So you could go and do root locus controller design for a DC motor, also frequency domain controller design for a DC motor. Here an introduction to controller design in frequency domain, but this is like more like a course if you wish. But basically those are the tutorials which I recommend you to go over them. The Simulink model also you have it, and it is very guided, that's why I don't want to go over them. We'll go later on exercises similar, but also those are different exercises, so I'll do with you different exercises. Those are important, you could go and look over them. Okay, and very guided, also you can download download them actually and work on them directly. So again, root locus, frequency response, and in here it is both together like lead lag compensator, and they compare the control effort for in case you have lag or lead compensator, what's the control effort in both cases. So it's important. Okay, here also it's a good example, but it's somehow advanced later on when we take modern control LQR regulation to be able to do a comparison. But for now you could go and check feed forward control, compare it with integral feedback control, and how this will compensate the disturbance in the system. Later on you will see the LQR regulator and you'll be able to compare performance of all together. Okay, this is also an important one. You could look at it now. Or so one last thing, um, we want to show is the bandwidth. Most analysis and design in frequency domain is done using the open loop, as we know, with only one exception. So we need to do the analysis and design in closed loop in this exception, which is the bandwidth. If you want to know the bandwidth of your system, you need to have the closed loop Bode diagram. So all the analysis and design for the controller, you use the open loop except for the bandwidth. What's the bandwidth? Bandwidth is, as defined here, is the frequency at which the closed loop, so here that's why I'm saying closed loop now. See, the closed loop magnitude plot drops to -3 decibel below the DC magnitude, and that's what we call bandwidth. Okay, is the frequency at which the closed loop magnitude plot drops to -3 decibel below the DC magnitude. That's the definition of the bandwidth. So basically, as you can see in here, so assuming this is your closed loop Bode diagram, you go to -3 decibel, so which is here, and then you find the frequency, and this frequency is the bandwidth frequency of your system. Okay, alright, so this is your bandwidth frequency. So which is a measure of the system, of the system speed of response. Which system? The closed loop system. The speed of response of the closed loop system, and it is related to the gain crossover frequency. If you wish, the bandwidth frequency also related to the gain crossover frequency, which is at 0 decibel in open loop. Alright, here is, I'll be showing you the relation. If you go, in this link, if you wish, you can see here the relation, starting from the fact that definition of it drops to 70. Well, 70 likes because it's -3 decibel is 0.7, so 70%, right? So that's from where it came, the 70. And they did the analysis, the calculation, which is not required, but well, you can find a relation between the bandwidth actually and the natural frequency for a second order system. And if you look to this relation, we didn't introduce actually in time domain the rise time, how it is function of zeta. Actually, this delta is the damping ratio, which is zeta. We usually use the zeta symbol. But from this relation also you could conclude that the bandwidth in the frequency response is inversely proportional to the rise time. What it means if you increase the bandwidth, you will decrease the rise time, so you make your system faster also, so in another way. And the exact relation between them is 0.35 if you wish, so according to here. So you can, and this is in the case of when your system response resembles to a low pass filter. When your system response in closed loop resembles to a low pass filter, you can have a relation between, if you wish, this omega b equal to 0.35 approximately tau, or tr if you wish. This is a relation between them. This when your system closed loop behaves this way. So you could use this approximation as well, in case it's needed for your design sometimes, or at least to know about it. Actually, you can relate them together, and this relation came basically from here. because also rise time is somehow related to here, okay, to this function here, which we didn't take in usually we didn't see an expression for rise time when we did time domain analysis, but I'm telling you it's somehow similar to this. Alright, so now we know what is bandwidth and how is it related to the gain crossover frequency. What's the gain crossover frequency? Is the frequency when you have 0 decibel. Okay, it's related to S. If it's omega n, we saw the relation in the link, web link anyway, okay? And how that's how it's defined. So the only analysis we require to do in closed loop is when we need to find the bandwidth of the system, which a measure of what, of the speed of the response as well, of the closed loop response. Okay, but we know in general we can, because it's related to the gain crossover frequency at the end, which is here. So if we speed up this, then we are increasing the bandwidth of the system. Good. So yeah, just to fix the idea at the end, those are your design requirements. So you do the analysis. So now we're able to do the analysis in addition to the bandwidth analysis, time, rise time, how it's related to the bandwidth related to the gain crossover frequency, in addition to all the analysis we saw in steady state and transient response. So that's the first step in our analysis, so we know which controller we need to design. Second, we draw the open loop transfer function, so we design our controller, so and using the CISO tool. So we'll see later on, as the example I showed to you and many in the Michigan University control tutorial. So it's an interactive tool, the CISO tool, so you can increase the gain, add poles, add zero, add lead, lag compensator, exactly as we did many exercises in time domain. Now we will do many exercises in frequency domain, but the theory is, that's how we covered the theory this way. To conclude or to do a comparison, here I'm putting for you like the advantages of frequency response and advantage of time response. Of course, all of those are credited to Prof. Rick Hill from his YouTube channel. Okay. So advantage of frequency response: richer source of information, as we know now, settles ambiguities from root locus, specifically for non-canonical system like higher order dynamics, numerator dynamics. You have zeros. Okay, so those are non-canonical systems. So settles these ambiguities came from the root locus analysis, which we know about. Okay. Richer source of information, we know that, so we can have higher order system prediction and so on. Good for experimental derivation. For experimental derivation of a model, we do it in frequency response, because it give you more richer information. Usually we do frequency analysis. If you go and any system you want to experimentally find it, directly recommend frequency analysis to get the function of or the model of it. But advantage of time response is give the result directly in the time domain, so you don't need to do this analogy, okay, between both, seeing, okay, so we don't need, because it gives you directly the result in time domain, which what we want actually. Okay, that's it for this chapter. Now we'll do more exercises using body plot or CISO tool.